Hi everyone, this is Kalyan Kumar and welcome once again to Chemistry Universe. We finished geometrical isomerism in the last video and today it is the time of optical isomers. Now optical isomers is a part of stereoisomers which in my experience as a teacher I have always found that it is perhaps the least understood of all the stereoisomers because the two isomers look almost alike. And when I say almost, that is a very slight difference. And this slight difference sometimes exhibits itself in the form of a huge variation in their properties. So in this video, I'm going to basically explain what is optical activity. And then in the future videos, we're going to talk about optical isomers. So this is only for optical activity to understand what is a non-polarized light, what is a polarized light, how does a polarimeter work, and what are these compounds that we are going to call as optically active compounds. So let's get on with it and start doing optical activity.
Light is an electromagnetic wave where the electric and magnetic fields are oscillating perpendicular to the direction of movement of light. Light from a source vibrates in many planes. Light vibrating in many planes is called unpolarized light. However, it is possible to make light vibrate in only one plane. Now, if we look at the light directly from the source, the vibrations seem to go up and down like this. So, this two-headed arrow can represent the vibrating plane. Light wave in a single plane is called polarized light. Now, we will pass this unpolarized light through an instrument called the polarimeter. The polarimeter has got two polarized filters. The first one is called a polarizer and the second one is called an analyzer. When light passes through the polarizer, the light that is passed through vibrates in only one plane. The other vibrations are either completely or partially cut off. The emerging light vibrates in only one plane and hence it is polarized light. Polarized filters have molecules arranged in a specific order that allows a light to pass through in only one plane. If the alignment of the polarizer is same as that of the analyzer, then we will see light glow through the eyepiece. Now the polarized filter of the analyzer is rotated through an angle of 90 degrees such that the analyzer's molecules are now perpendicular to the plane of the polarized light, resulting in no vibrations passing the analyzer, and we see darkness in the eyepiece. Now, if the polarized light is passed through an optically active compound kept in the sample tube, then the plane of the polarized light rotates and hence the darkness in the eyepiece is not there anymore. Darkness only exists when the analyzer is exactly perpendicular to the plane polarized light. We rotate the analyzer till we see darkness again in the eyepiece. This occurs when the analyzer is perpendicular to the plane of the rotated light. Let's assume that the initial direction of the plane polarized light coming from the polarizer is this. In the beginning, the analyzer is kept parallel to the polarizer and hence all the light will pass through the analyzer too. If we rotate the analyzer, by an angle other than 90 degrees, some light will still pass through, but its intensity will be reduced. But if we rotate the analyzer by an angle of 90 degrees to the initial direction, then the entire light will be cut off. One of the most accurate and commonly used polarimeter is the Lorentz Halfshade Polarimeter. It consists of a monochromatic source S, which is placed at a focal point of a convex lens L. Just after the convex lens, there is a Nicol prism P, which acts as a polarizer. H is a half-shade device which divides the field of polarized light emerging out of the Nicol P into two halves of perpendicular plane. T is a glass tube in which optically active solution is filled. The light, after passing through T, is allowed to fall on the analyzer Nicol A, which can be rotated about the axis of the tube. The rotation of the analyzer can be measured with the help of a circular scale C, and this E is the eyepiece. To understand the need of a half-shade device, let us suppose that half-shade device is not present. The position of the analyzer is so adjusted that the field of view is dark when the tube is filled only with deionized water. The position of the analyzer is noted on a circular scale. Now the tube is filled with optically active solution and it is set in its proper position. The optically active solution rotates the plane polarization of the light emerging out of the polarizer P by some angle. So the light is transmitted by the analyzer A and the field of view of telescope becomes again bright. Now the analyzer is rotated by a finite angle so that the field of view of telescope again becomes dark. This will happen only when the analyzer is rotated by the same angle by which plane of polarization of light is rotated by optically active solution. The position of the analyzer is again noted. The difference of the two readings will give you the angle of rotation of plane polarization. A difficulty is faced in the above procedure that when the analyzer is rotated for the total darkness, then it is attained gradually and hence it is difficult to find the exact position correctly by which complete darkness is obtained. For example, if the total darkness is attained at 20 degree clockwise, then at 19.9 and 20.1, it will be difficult to tell which is more darker than the other since there is nothing to compare it with. The half-shade device consists of two semicircular halves of equal size. One half is made up of plain glass and the other is made up of quartz. Without going into too much detail as we are talking about this experiment from the point of view of chemistry, it will suffice to say that the plane polarized light coming out of the glass will remain in the same plane while that coming from the quartz will get rotated by 90 degrees. When no optically active substance is present, if the principal axis of the analyzer is parallel to that of the polarizer, the glass half becomes bright while the quartz half becomes dark. If the analyzer is rotated by 90 degrees, then the quartz half becomes bright and the glass half will be dark. The analyzer is kept exactly midway between these points where both halves will be equally bright, and this brightness will be lower than the maximum brightness of each half individually. It is easier to compare two bright semicircles rather than try to achieve complete darkness of bright circle absolutely. This is the Lorentz Halfshade Polarimeter. Prepare the solution of the substance whose optical activity is needed to be determined. Next, clean the polarimeter sample holder with deionized water. Next, we must calibrate the polarimeter with deionized water. To do this, we must fill the sample holder up to the top with deionized water and ensure that there are no bubbles. Next, open the hatch to place the sample holder. Close the hatch and observe through the eyepiece. To ensure calibration, make sure the two semicircular halves are of equal brightness. Make sure that the inner and outer scales have the zeros aligned. If not, align them by moving the inner scale. This implies that the machine is calibrated. Next, after discarding the deionized water, fill the sample holder with the solution of the sample. Place the sample holder in the polarimeter. As done before, adjust the dial to see the two semicircular halves with equal brightness. Now note the value of rotating using first the outer dial. The outer scale is the whole number for the observed rotation reading, and the inner scale is for the first two places of decimal reading. Look for the outer scale reading which meets up with the 0 of the lower scale reading. If it exactly meets a line, then note the value of the outer scale. If it is in between two values, then use the lower value. In this example, the whole number is 1. To know the decimal point, look at the mark on the inner scale that exactly matches a mark of the outer scale. In this example, the decimal number is 1. So in this case, the reading is 1.1. If you take the reading on the left side of the machine and the inner scale 0 is above the outer scale 0, then the rotation is negative. And if you take the reading on the right side, then it will be the other way around. Meaning if the 0 of the inner scale is below the 0 of the outer scale, it is negative reading. Why are chiral molecules optically active and achiral molecules not? We need to understand certain points. First, a molecule that has a net dipole moment will rotate the plane polarized light, and it will do so always. Just because molecules of a compound rotate the plane polarized light does not make the compound optically active. A molecule not having a net dipole moment will not rotate the plane polarized light. A molecule that has net dipole moment has an electric field. This electric field vector interacts with the electric field vector of the plane polarized light and by some mechanism rotates its plane. The mirror image of a molecule having net dipole moment will always rotate the plane polarized light in the direction opposite to that of the molecule. Now let's take an example of an achiral molecule. It is achiral because it has a plane of symmetry. Let us assume that a plane polarized light approaches this molecule from the front side. And let us say it interacts with the molecule from the front. And let us also assume that as it passes through this molecule, it will get rotated because the molecule has a net dipole moment. Let's also assume that this light is rotated to the left, like this. If you were to reverse this animation, it would tell us what would this light behave if it were to approach this molecule from the back. If this light were to approach this molecule from the back side, in between these two white atoms, it will move towards the green. Therefore, when it passes through this molecule, it moves like this. And let us assume that in front of this molecule, after light has been turned to the first one, you find the mirror image of the molecule. So now it is going to approach the second molecule in this direction. And since it has already been turned by the first molecule, it will now move towards the green as it did so in the first one. And therefore the molecule rotates it such a way that it moves towards the green and the plane becomes the same as the one before hitting the first molecules. So in this case, in the A chiral molecule, the mirror image of the molecule is going to cancel the rotation of the first molecule. And statistically speaking, that out of several billions and billions of molecules, that there is always a mirror image existing for each and every molecule. So in effect, the net optical effect is zero. So even though each molecule did rotate the plane polarized light, either clockwise or anti-clockwise, the net rotation is zero and the molecule is said to be optically inactive. Now let us take the example of a chiral molecule. As you can see, this molecule does not have any plane of symmetry. Let's assume that a plane polarized light hits the molecule from the front side. Once it passes through, let us also assume it tilts towards the olive atom. Which means when it approaches the molecule from the back side, that is in between white and olive, it will tilt towards the white and therefore go back to vertical. So now it turns left after meeting molecule 1. Now in a sample of a pure chiral molecule, the molecules will not be mirror images of each other. Therefore, it will encounter a same molecule which is not a mirror image of the first one. Now this molecule is just this molecule which has been rotated. Remember, the light when it passes through this white and olive, it will tilt towards the white. So when this light approaches the second molecule, it is going to move towards white, which implies that the optical rotation is enhanced. So whatever is the rotation of the first molecule, the second molecule doubles it. So there is no cancellation of optical rotation. And this also proves that the optical rotation is directly proportional to the number of molecules it interacts with.
Now that you have seen optical activity at work, now we're going to look at the properties on which the theta, the angle by which an optically active compound rotates a plane polarized light, depends on. So optical rotation of a solution, theta in degrees, is directly proportional to concentration. Now this intuitively makes a lot of sense. More the concentration means more is the number of molecules per unit volume, and therefore when it passes through a certain amount of the solution, obviously it will encounter more molecules and there will be greater rotation. And it is also proportional to L, and let's understand what L is. First, let's understand what is C, because concentration can be expressed in various ways. Here, the C is the concentration of the solution in gram per ml, while the length L is the length of the polarimeter tube in decimeters. Now remember, the length of the polarimeter tube also is very important in measuring the optical activity of a compound, because for a given concentration, longer the polarimeter tube is, again more molecules the plane polarized light will encounter, and greater will be the angle of rotation. And the reason we use it in decimeter is because of the particular equation that I'm going to show you. Of course, you can use any unit for that. Appropriately, the units of theta will change. 1 decimeter is 10 centimeters, as we all know. And theta is proportional to C into L. And theta is now, I'm going to use a constant of proportionality, which is written as alpha. And this is the lambda and this is T degrees Celsius, and they are only telling you at which lambda we measured it and at which temperature in Celsius we measured it, C into L. And what is this this alpha is theta upon Cl. So what does this alpha represent? It is called specific rotation of a compound. So specific rotation is a property of a compound. Different compounds will have different specific rotations, and specific rotation is unique for a compound. Of course, it is possible that two different compounds may end up having by coincidence the same value of specific rotation, but then that is coincidence. It does not mean anything in terms of the properties or the relationship between the two molecules. But in general, this coincidence is very, very improbable, and therefore you will find that almost all the compounds have unique this particular specific rotation. And what does this specific rotation mean? It is the rotation of an optically active compound which is having a concentration of C which is equal to 1, and remember C is in gram per ml, so I take 1 gram per ml, and the length of the tube is 1 decimeter. So when I keep all others as unity, the angle of rotation of the compound at that point is called specific rotation. Therefore, alpha is fixed for a given solute. Theta can be changed by altering concentration and length of the polarimeter tube. So what is lambda? Lambda is the wavelength of the monochromatic light used, and T is the temperature in degrees Celsius at which the experiment is conducted. Now remember, theta increases with increase of concentration. Makes sense, it is directly proportional to C. Theta also increases with increase of the length of the polarimeter tube we discussed. More molecules it meets. And theta increases with temperature. Now this is something which is not intuitive, and this is not easily understandable because we need to get then into the nitty-gritty of how a molecule rotates the plane polarized light. What is the mechanism of doing that? And those involve complicated mathematical equations which we are not going into it, because right now we are talking about optical rotation with respect to chemistry. So, and it seems that increases with the decrease of wavelength of the monochromatic light source. That means you increase the frequency or decrease the wavelength, you find optical activity, the angle of rotation to be higher. So with that, we come to the end of this particular video. I hope you were able to understand what optical activity is and understand how the polarimeter works. In the next episode, we are going to discuss about symmetry and symmetry elements, which are very, very important in understanding the optically active compounds. So with that, this is Kalyan Kumar signing off. Have a wonderful day. Goodbye, and thank you for watching this.